Hey guys, welcome back to another video of AP Chemistry. This is our last video for our lessons. It's Unit 9. We're going to be talking about electrochemistry today. Alright, so starting with some vocabulary, we'll talk about coupled reactions. We'll talk about galvanic and electrolytic cells, reduction and oxidation, which we talked about before, but it's going to be very important here. We'll talk about the anode, cathode, and salt bridge, cell potential, and current. Okay, so this unit will tie into physics quite a bit just because of the electrochemical aspect. All right, so coupled reactions. So in thermodynamics with Gibbs free energy, we had favorable and unfavorable reactions, right? So what we can do is we can pair these unfavorable reactions with favorable ones to make it overall favorable. Okay, so these coupled reactions always have a common intermediate to drive the reaction. So you can see here from this example, right, we have two reactions. Our first one has a negative delta G. Our second one has a positive delta G. Remember, negative is spontaneous, it will happen on its own. Positive is non-spontaneous. So our first reaction, we have 2Fe2O3 goes to 4Fe plus 3O2. The second one is carbon plus O2 goes to CO2. We have a common intermediate there, okay? So what we can do is we can combine these reactions, right? Like how we've been doing with Hess's law, essentially. And what happens is our delta G overall becomes negative. So coupling these two reactions, even though the second reaction is unfavorable, it will still go when it's paired with this first one, okay? So some terms, these terms I haven't seen used a lot, but they are good to know. We have exergonic and endergonic. This is the same thing as exothermic and endothermic, but for Gibbs energy, for spontaneity. So exergonic is spontaneous, endergonic is not spontaneous. Okay, so those are the energy profiles for those two. Okay, so what happens in our coupled reactions, so this is an example that happens in the body. For converting glucose to CO2 and water is an exergonic reaction. However, converting amino acids to polypeptides is an endergonic reaction. When you couple them together in the body, it's a net exergonic reaction. The net reaction goes downwards. It'll happen when it's paired together. Okay. All right, so for electrochemical cells, these are cells that transfer electrons. We're specifically looking at the electrons here. Okay, so when the electrons are moving, this can generate electrical energy or current. Okay, there's two types of cells based on thermodynamic favorability. The first is galvanic cell. We'll focus on that more than the other one, but galvanic cells are favorable. These will happen on their own. Electrolytic cells are unfavorable. Okay, so favorable means delta G is negative. Unfavorable, delta G is positive. Okay, so you'll see with this electrolytic cell, we'll need some sort of battery or some sort of power to make it happen. Okay, and before we get into the parts of the cell, we'll need to know the definitions for cathode and anode. So a cathode and anode is going to be the two sides of the cell. It's the two substances or the two chemicals we have in there. The cathode is going to gain electrons, and it's going to be overall negative. And it's going to have some positively charged ions. Okay. The anode is the opposite. It's going to release electrons. It's going to be positive, and it's going to have negatively charged ions. Okay. So make sure we know the difference between cathode and anode. Those are important. So when we're talking about a galvanic cell, remember these are favorable. You're going to have two metals in solution. So you can see those here. Those little pieces, that gray one and the red one on the other side. Those are our metals. Okay. On the left we have zinc in this example. The right side we have copper. Okay. So in this case, if we zoom in a little bit, our zinc is losing electrons. You can see the arrows pointing in the direction of the electrons, and it's making a cation to go into solution. The copper, on the other hand, so I moved to show that, so that's going that way, and then we have zinc going in solution. The copper is gaining electrons, and the copper is going inwards. You can see that arrow pointing there. Okay, so copper is getting plated onto the middle. Okay, so if the zinc is losing electrons, it is oxidized. Okay, so this is the anode when oxidation happens, where they're losing electrons. Okay, the cathode, the other side, is the copper because it is being reduced, right? Because it's gaining electrons, so it's being reduced. That makes it the cathode. Okay, so electrons in galvanic cells will flow from anode to cathode. Right, and then there's a summary for the anode and cathode. So anode is oxidized, the electrons are being lost, and when electrons are being lost, the ions go into solution, so the mass decreases. The cathode is opposite, it's going to gain electrons, and then since the ions from solution are plated on the middle, it's going to gain mass. Okay, so this is going to stop when you run out of anode, because that's what's going into solution. Okay. And a way to remember this, if this helps you, an ox and red cat. So an oxidation is loss at the anode, so anode oxidation. Red cat is reduction cathode. Okay, so if that helps you, great. If not, try to find a way to remember these. Okay. So in a galvanic or an electrochemical cell, we also have what's called a salt bridge. That's this tan U, upside down U, or the N-shaped thing in the middle there. Okay. What the salt bridge does, let's zoom in so we can see what's happening. So you can see as the zinc is coming out, there is sulfates going into that solution. And as the copper's leaving, potassium's going to replace it. Okay. So what the salt bridge does is it's just balancing out the charges. Okay. So it's made of ions to balance out charges. Because if we don't have something to balance out the charges, it's going to stop working. It's not going to work well for us, right? Okay. So the way the charges are going to move is the cations, so our K plus, is going to go to the cathode, and ions, our SO4 2- goes to the anode. Okay. If that's a lot to remember, just figure out what's happening in the cell. Then if a positive is coming off of the middle, the negative needs to go to balance it out. Okay. If a positive is being taken up, a positive has to go to replace it. Okay. So the total reaction, it is a redox reaction, so we can write these half reactions like we've done before. Okay. So with the zinc, we said it's losing electrons. In this case, it's losing 2 electrons. So zinc solid becomes zinc 2+ ion plus 2 electrons. The copper, we said, is gaining electrons. So copper 2+ plus those 2 electrons becomes copper solid. And this is the net ionic equation that's happening there with the balanced electrons. Okay, so this is something that's common with electrochemical cells. You often have to write half reactions for what's happening there and identify the anode and cathode. Okay, so because electrolytic cells are, so that was for galvanic cells. For electrochemical or electrolytic cells, these are unfavorable, right? So we normally have to have a current applied. So you can see here in this picture on the right, we have something that's plugged into an outlet to provide the power for these electrons to move. Okay, so the result is that the reaction is reversed. So we're going to go the other way, and and charge and definition. Okay, so oxidation still happens at the anode, reduction still happens at the cathode, but what the anode and cathode are is reversed. So remember, we had in galvanic cells, the anode was negative, cathode was positive. Now it's the opposite way. Anode is positive, cathode is negative for electrolytic. Okay, so there's some information down here, summary for both of those to help you out, to help you understand what's happening. Okay, you can also see that our half reactions look a little different there because something different's happening. Okay, so what I would suggest doing, because these are 2 different cells, I would remember what happens with a galvanic cell, understand that completely. Then electrolytic cell, you're just flipping it. Okay, that might be the easier way to remember these. So with these electrochemical cells, we will have a potential, an electrical potential. Okay, these are determined by the standard reduction potentials. This is something that's given on a table. You won't have the table on your AP test, so if you need these numbers, they'll be given to you either like this next to the reactions, or they'll be given to you in a chart and you have to figure out which ones you need to use. Okay, but each reaction comes with a cell potential or reduction potential. And notice here, our reactions are being reduced. They're gaining the electrons. Okay, that's where they're reduction potentials. So what we need to do is we need to figure out which one we need to flip. Okay, so in this case, our cell that was oxidized is the zinc, so we flip the zinc. So instead of being negative, and we flipped the reaction and we made it positive. Okay, so if you invert the reaction, you need to change the sign. If you don't have a reaction, like a cell, an image to go off of, and you need to figure out which one to flip, and a galvanic cell, it's going to be favorable. So for favorable, we want a positive E. Positive is favorable. So between these two, if we want an overall positive, we have to flip the negative one. Whichever one's more negative is what you flip. An electrolytic, that one is unfavorable, so you do the opposite again. All right, so what's happening here is we flipped our oxidized cell. And then since we have our two reactions, we can find a total E cell. That's our cell potential for this galvanic cell. Okay. One note here is that cell potential is intensive property. So even if you have to bounce out the electrons on the left side, if you have to change the coefficients or anything, that does not affect your cell potentials. Okay, so you cannot change these numbers. Do not change these numbers here. You can only change the sign if you flip the reaction. Okay, and remember in galvanic cell, we want it to be overall positive. Okay, so with these cell potentials, right, we said positive is spontaneous, negative is non-spontaneous. Since there's a correlation there, we can make an equation out of it. So our delta G for spontaneity is equal to negative NF E cell. Okay, that symbol on top, that's called a knot. It just means the standard conditions. You don't have to worry too much about that. Okay, but so what we're doing here is we have an E cell for the reaction. Your N is the number of electrons. It is not moles. It is your number of electrons that were moved around. F is Faraday's constant. It's a constant. It stays the same. And then E cell is that cell potential that we just found. Okay. So our delta G is negative, our number of moles here, number of electrons, I just got them mixed up. So the number of electrons that we had comes from the charge. We had a +2 charge, we know 2 electrons moved. So that's a 2. You can also get that number from your half reactions, right? You can see the electrons there and bounce it out there. So we have an N of 2, number of electrons is 2. Faraday's is 96,485 coulombs per mole. That's C is a coulombs. And then our E cell is 1.10. So we can do that math to figure out our delta G. So let's go ahead and do that. We have negative 2 times 96,485 times 1.1. So our delta G is equal to negative 212,267, and this is just going to be in joules. Okay. All right, and then the last thing we have is Nernst and Faraday. Okay. So for this part, for a non-standard condition, the molarity of the solution affects the voltage difference. Okay, so the Nernst equation is used to show that. That's this equation here. This equation is given on your formula sheet, so is the previous one. Okay, all the equations for this unit are given to you. This equation, so remember I said that naught is a standard. So if we need to find it for non-standards, we're going to use the standard conditions. We're going to use RT over NF. So R and F are constants. N is your number of electrons. T is your temperature. And then we have ln of Q. Q was from equilibrium. That was your, the Q was your reaction quotient. Okay, so we know how to find that. So products divided by reactants at wherever you're at, not at equilibrium. So we can do that to find our E of the cell when it is not at equilibrium, when it's at non-standard conditions. Okay, and then the last thing is Faraday's law. Faraday's law relates the amount of substance, so grams or moles of how much you have, to the charge. Okay, so we have this equation, I equals Q divided by T. I is your current in coulombs per second. Q is your charge. T is your time. Okay, so we can use this to know, if we know how many moles of electrons are being moved, we can figure out the number of coulombs being used. Okay, so we can do this example down here. If we have this cell, which is chromium 2 plus 2 electrons goes to chromium solid. And if we know that 0.86 grams of chromium is plated on this faucet in 12.5 minutes, we can figure out the current that's needed. Okay, so we're going to start with the mass that was given to us. We have that 0.86 grams of chromium. Okay, I'm going to put it over 1 because that's what we're starting with. And then we can get 2 moles of chromium using its molar mass, which is 51.996 grams per 1 mole. And then for 1 mole of chromium, we know how many moles of electrons we used. So for 1 mole chromium, we have 2 moles of electrons. So that's how we get from our substance to electrons. And then we know for electrons to coulombs, okay, because coulombs is going to be part of your current, we use Faraday's number, Faraday's constant, which is for each 1 mole, there's 96,485 coulombs. Okay, so from this, we can find the number of coulombs that were used. So we have 3,191.67 coulombs of energy. Okay, then we can take it to find the current. Current, I, is your charge in coulombs divided by your time in seconds. Okay, so our charge in coulombs we said was 3,191.67 coulombs divided by, we need a time in seconds. We have 12.5 minutes. So 12.5 minutes times 60 times 60, because there's 60 seconds in a minute, is 750. Okay. So if we do that math here, our 3,191.67 divided by our 750 seconds is 4.26 coulombs per second, capital C. Okay. This question did not specifically ask for it in the current in seconds, so you could use 12.5 minutes on the bottom and just report in coulombs per minute. That should be fine there. Okay? But that is it. You have learned everything now for AP Chemistry. After this, all we're doing is we're just reviewing for that AP test. So fortunately, these last few units kind of incorporated quite a few parts of it. So a lot of equilibrium was used, a lot of thermodynamics was brought up, stoichiometry. So hopefully that helped to help you remember parts of first semester and help you connect everything together. But after this, we're just going to be reviewing. So make sure you come to class prepared to review. We'll take some practice tests, see what we need to work on. And a lot of it's going to be for you to study as you see fit. Okay. So there's going to be some parts that are directed by me as usual, but a lot of it's going to be self-guided. So if you need any help, if you have any questions, let me know. But go ahead and start looking through your notes again. Go back through the previous units, especially semester 1, and start studying up. All right. I will see you in class. Have a great day.